In my experience as a data scientist, the chi-square test and all of its variants are often either overlooked or misapplied. In this lecture, which took me more time than usual to prepare, I hope to present to you the chi-square distribution and its associated applications. Therefore, we'll be discussing the chi-square test of independence, the chi-square goodness of fit, and the chi-square homogeneity of proportions. And we'll be doing examples in RCommander. So the first essential aspect of understanding chi-square is to understand the pronunciation. Many would assume that the pronunciation is chai or chi. Neither is correct. The proper pronunciation is chi. So make sure you always get that correct when, discussing this particular distribution and its application with your contemporaries. So let's examine how the chi-square distribution appears when graphed. So above, we have a graphical representation of the chi-square distribution. And what you see being illustrated is the probability densities of the various chi-square distribution based on the degrees of freedom. So as you can see, depending on the degrees of freedom, the distribution will shift about. So here's a couple things to remember about the chi-square distribution. The sample should be from a random population. Each observation should be independent from the other, and all cells must have a frequency of at least 5. And what this means will become evident as we continue to go through the slides. So first, we'll discuss the chi-square test of independence, which is probably the most frequent application, the most common application of the chi-square distribution methodology. So the purpose of the test of independence is it examines whether two categorical variables are independent of each other, whether knowing the value of one variable gives you information about the other variable. Does one variable depend on its association with the other variable? And is there association between gender and voting preference? And that is a example that you could potentially apply. But for our example, we're not going to be doing gender and voting preference. We're going to be doing the classic obesity and smoking example. And this is in a lot of statistics textbooks, which is why I selected it for our example here. Now, you'll see that this is not correct. Each cell should contain at least 5 observations. So we should have 5 observations here or more, 5 observations here or more, 5 observations here or more, or 5 observations here or more. And as you can see, we don't have those number of observations. So this would actually be an incorrect application, but we're going to just roll with it because this is the example that I've selected. So in theory and in practice, when you're doing your own chi-square test of independence for your class or for your research, make sure each one of these cells has more than 5 observations. So 5 observations or greater than 5 observations. So 5 or greater, okay? So this is a contingency table. We went over this in a prior lecture. It's also known as a cross-tabulation or cross-tab or two-way table. And it's an arrangement in which the data is classified according to 2 categorical variables. All right, so the categories for one variable appears in the rows and the category for the other variable appears in the columns. Each variable must have 2 or more categories. So you don't necessarily have to have a 2x2 table. For the case of our example, we'll be doing a 2x2, but you can have additional categories if necessary. And each cell reflects the total count of cases for a specific pair of categories. So this data that you have over here in the right-hand corner, this is found in the video description along with any code associated with this particular video. But as you can see here, we have categories. We have smoking and obesity. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 unique individuals. So there, in our case, we have 10 unique observations. And each one of these observations, for our case, is a unique individual. So these individuals could either be smokers who are obese, non-smokers who are obese, so we have non-obese, non-smokers. Actually, let me go back to this because it'll be more evident if we look at it here. We either have smokers who are obese, smokers who are not obese, non-smokers who are obese, and non-smokers who are non-obese. So of our 10 individuals, Each individual needs to fit into one of these categories uniquely. So either you're an obese smoker, a non-obese smoker, an obese non-smoker, or a non-obese non-smoker. All right, so each one of these counts pertains to a unique individual. There can only be 10 total because there are only 10 individuals in our survey. Okay? So some folks get confused by this. Try not to get confused. Watch this part over again if there's some confusion. We have 10 unique individuals, and each individual is categorized by how they fit in each one of these particular categories. So how they fit as within the smoking category and how they fit in with the obesity category. So what we want to do with this particular test of independence is we want to test for significance of association between smoking behavior and obesity. And we're going to be using the chi-square test of independence, and we're going to be assuming an alpha value of 0.05. So here is our hypothesis. It's either variable 1 is independent of variable 2, or variable 1 is not independent of variable 2. And for our particular example, this is smoking is independent of obesity, or smoking is not independent of obesity. All right, so here's how we would run this particular application of methodology in RCommander. We would go to our RCommander menu. We would select Statistics, Proportions, to Sample Proportions Test. We have to select our groups, and we have to select our response variable. Okay? Then we have to select our hypothesis, our confidence interval, and our type of test. Leave this as is. Typically, these are going to be two-sided. For our examples that we're going to be covering in this particular lecture, we're going to always assume that we're doing two-sided. And our confidence interval, you'll have to determine what that's going to be based on what the alpha value is for your experiment. Our alpha value is 0.05, so our confidence interval will be 0.95. There's a lecture on that in this playlist if you need help determining confidence interval and alpha value. So here is our output that is generated if we follow those particular steps using the data which is available to us. We have our chi-square value, our degrees of freedom, and our p-value. So as you can see, our p-value is 0.2598, which means it's greater than our alpha value of 0.05. So we do not reject the null hypothesis. So this is how we would write our findings. A chi-square test of independence was performed to examine the relation between smokers and obesity. The relation between these variables was not found to be significant. Remember, because our p-value is greater than our alpha value. So it was not found to be significant at the p less than 0.05 level. X squared, open parens, 1. 1 is our degrees of freedom, okay? N equals 10 because there was 10 observations. Remember, 10 observations. So the number of observations, N equals, so N equals 10 because there was 10 unique observations that were then split between those categories, the row categories and the column categories. This value right here, 1.27, that is our R squared value, or excuse me, our X squared value, or our chi-square value, as it were. Okay, so our chi-square value, 1.2698, we round that off. That is the value there. And this is our p-value right here, rounded to 2 decimal places, p equals 0.26. And because our p-value is greater than our assumed alpha value, we do not reject the null hypothesis, and we find that the relation between these variables was not found to be significant. If p was less than 0.05, we would find the relationship to be significant. Here's another way to do it. Statistics, contingency tables, enter and analyze two-way table. Here you have to name the row variable and the column variable. We selected the number of rows to be 2, the number of columns to be 2. And remember, as I mentioned before, you're not always set to 2 by 2. It depends on what the situation is, and then from that, you would then apply what is necessary. With a McNemar's test, you are stuck with 2x2 contingency tables, and we'll discuss that in our next lecture. But for this, you can select the number of rows, the number of columns. We name the rows appropriately, we name the columns appropriately, and then we enter our values. Remember, there's 10 unique individuals. And you can also type in here, if you so choose, what you want the outcome to be. If it's binary, it's yes, no, yes, no. So this would be obese, our row values, yes, no, and our smoker column variable values, yes, no. And then you would click OK. Actually, first you want to click the statistics tab. And we're going to select no percentages, chi-square test of independence, because remember, that's what we're seeking to utilize here, chi-square test of independence. And once we have that selected, we click OK. Here's our outcome. It's the same outcome as before. We just went about it in a different way. And all the values that were found within our output, you would then just place those values in the appropriate spots so the APA format guidelines are satisfied for chi-square. All right, so let's move on to the chi-square goodness of fit. So for the goodness of fit, this test is going to evaluate whether the observed frequency distribution of a categorical variable matches an expected distribution. Does the observation data fit a particular distribution? Does a and here's an example, does a six-sided die produce each number 1 through 6 with equal probability? All right, so let's go about determining how the goodness of fit model is actually what it's actually seeking to determine by going through an example. So here we are. Here's our goodness of fit example. And this will hopefully make clear as to what we're seeking to achieve with this test methodology. So we have a small motel owner, and he's created his own predictive model. And he wants to see if this model is useful as it pertains to the reality of the situation. So he has a model, and we want to know if the models that was created by the motel owner are equal to the observed guest frequencies. So we were just doing this, if this were for your needs, you just need to fill in whatever your variables are as it relates to this hypothesis here. It's the observed frequencies are equal to the expected frequencies, and the alternative is the observed frequencies are not equal to the expected frequencies. So in this case, the owner's model frequencies are equal to the observed guest frequencies. The owner's model frequencies are equal to the observed. This should actually be the owner's model frequencies are not equal to the observed guest frequencies, are not equal for the alternative hypothesis. That's a typo. In any event, so here is what the motel owner gives you. He believes, as far as traffic is concerned to his motel, that on Mondays, so this is broken down by days of the week, on Mondays he should expect to see 10% of the total weekly traffic, Tuesdays 5% of the total weekly traffic, Wednesdays 20% of the weekly traffic, Thursdays 10%, and so on and so forth. And as you can probably see, these values actually sum to 100%. Because remember, this is a weekly model. It's for the week. He wants to know the frequency of guests as it is broken down categorically by day of the week. So these have to sum to 100% because 100% of the guests are going to come on a week. But what is the frequency of that 100% as categorized by each day of the week? So of all the guests, 10% of those guests should come on a Monday. Of all the guests, 5% should come on a Sunday. So you sum all these percentages together and it's 100%. All right? So you calculate and keep track of all the guests as they come to the hotel each day of the week. So Monday, there were 11 guests. Tuesday, there were 25 guests. Wednesday, 30. Thursday, and so on and so forth. And if you sum these values together here, this is the value of the n that you're going to use for your APA format. So n equals 127, and that's what you're going to put in the APA format once we reach our conclusions, our output. All right. So if we were going to run this particular bit of data, the observations and the model within R, this is how we would do it. So here we have our model. These are our percentages. This is right here, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. Our sum is the model, all right? So that should sum to 100% if you were to assign all of these to model and then sum the elements within the model vector, you should come to the sum of 1 because these percentages will sum to 1, okay? The results are what actually occurs each day of the week. This is the number of guests on Monday, Tuesday, Wednesday, so on and so forth. So if we were to run this function here, chi-square-test results, this is what we actually observed. P equals the model. These are our expectations. Rescale P equals false. Why is rescale P equal false? Rescale P equals false because we had determined these values as percentages, okay? So we don't need to rescale because these are percentages that add up to 100%. And I'll show you when it's appropriate to rescale in our next example. But because we have percentages as our model variable, our model vector here, we do not rescale. So we have the percentages and then we have the observations. And we put it into this function, which is the goodness of fit test, and this is our output. So as you can see here, we have our x squared or our chi-square value. We have our degrees of freedom, and we have our p-value, which you can see is less than 0.01. So let's put this in APA format. So we perform our goodness of fit test. We assess the model's expected frequencies against observed frequencies, and we found that the difference was found to be statistically significant. All right. So the difference was found to be statistically significant at the alpha equals 0.05 level. So here is our degrees of freedom. Here is the number of observations. Here is our chi-square value, and P is less than 0.01. So it was less than our alpha value. So let's go back and look at our hypothesis. So we would reject the null, and we would say the observed frequencies are not equal to the expected frequencies. So if there was no typo here, we would say the owner's model frequencies are not equal to the observed guest frequencies. The owner's model frequencies are not, there should be a not here, are not equal to the observed guest frequencies, which means it's a crummy model. His model is not a good indicator because his model frequencies are not equal to the observed guest frequencies. We reject the null hypothesis. It's a crummy model. It didn't do a good job predicting what we would expect to see. And really, when you think about it, that's probably no surprise given the circumstances. Or maybe we have a statistical genius who is working as the model owner. Who knows? Anyway, let's do another example. Same thing. All right. I just want to show you how rescale works. And another example, if you're working in a situation in which you're not given percentages, instead you're given observations. So we're working with the model owners, the motel owners model again. So therefore, and we're using the same alpha value. So our hypothesis is going to be that the owner's model frequencies are equal to the expected frequencies, or the owner model frequencies are not equal to the expected frequencies. Okay. But in this instance, the owner instead collected the number of stays in the motel. In this case, he's not going by percentage. He's actually going by the number of individuals from which he observed. All right, so he observed 20 on a Monday, 28 on a Tuesday, 18 on a Wednesday, and so on and so forth. And he gives this to you, and he says, I believe that this, what I've observed previously, or this model which I created, is a good indicator as to what I should expect to observe in the future. So again, these don't sum to 100%. These are just the observations. All right. But here, when you come in as the statistician and make your own observations, this is what you see. So he expected to see 20 on a Monday, 28 on a Tuesday, 18 on a Wednesday. What you see is 14 on a Monday, 25 on a Tuesday, 22 on a Wednesday. And if you sum these values together, you come to the value of 149. So we sum all these values together and we get the value of 149. Now, n equaling 149, that is what you're going to report in your results, your APA results. So sum these values together, n equals 149, that is what's going to go into your findings. All right? So when we put this in APA format, n is going to equal 149. So in this case, this is the motel owner's model, 20, 28, 18, 25, 16, 22, and 26. And what we're going to do here are the results. We'll get to this in a moment. Here are the results. So this is the model. And this is what you observed, 14, 25, 22, 18, 16, 24, and 30. And each one of these corresponds to what you observed versus what was expected. Now, in this case, chisq.test, this is our function. Results go here. P equals model. Rescale equals true. Rescale equals true. What this is telling R to do is it's saying, turn this into a percentage. Turn this into a percentage as it relates to a complete whole. So sum all these values together, all right? And from that sum, you're going to divide, so whatever the sum of this is, 20 divided by the sum, 28 divided by the sum, 18 divided by the sum, 25 divided by the sum. And because each one of these values is divided by the sum, these values will then be scaled to percentages of that sum. You can do this in R. I'll show you how to do it manually, but this will do that for you. So it's going to rescale this vector, and it's going to turn each one of these observation values into a percentage. And then it's going to calculate it for you. So as you can see here, we still have a crummy model because our p-value is exceeding our alpha value of 0.05. It's greater than our alpha value of 0.05. So we're not going to reject the null hypothesis again. Degrees of freedom is 6. Chi-square value is 5.7582. We have to round these to two significant figures. So here are our findings. A chi-square goodness of fit test was performed to assess a model of expected frequencies against observed frequencies. The difference was not found to be significant at the p less than 0.05 level. Here's our degrees of freedom. Here's our number of observations. This is what you observed, not what the motel owner observed. Here is our chi-square value to two significant figures, 5.76, and here is our p-value. So if we wanted to do this in R, this is how you would do it. And you can test this on your own if you'd like. This is if you wanted to, instead of having R rescale these values for you, if you wanted to get an idea as to what R is actually doing, when it rescales, you would get the sum of the model. So we're summing the model, we're putting it into a value. And then each value, these are the values that the motel owner provided you. It'd be 20 divided by the model sum, 28 divided by the model sum, 18 divided by the model sum. And each one of these values would be a percentage, which would sum to 100%. And then if you'd like, you can then do this without having to rescale. If that's a path that you'd like to go. It's easier just to have R rescale these values for you. But if you are really wanting to see how it works on your own, you could do it like this. I would heavily recommend, though, doing it as was displayed in the previous bit of code. As you can see, it's the same outcome. All right. Should I go through this in R with you? I think that we should do it because there'll probably be some confusion, I suppose. So let me get R ready to go. Let me get R up here for you. All right, so let's go over this quickly. Let's see here. All right, so here are the values. Let's run this code. All right, so here's our model. As you can see, it sums to, we sum these values. It's 155. So what this is doing here, when we assign model sum, the sum function of the data vector model, we get the value of 155. So 20 divided by 155 is this value. 28 divided by the model sum is this value here, and so on and so forth. Now, if we were to run this bit of code here, and all of this is in the video description, you'll see that what we end up with is we end up with the percentages which sum to 100%. This is the percentages broken down for each week, each day of the week. So on Monday, we'd expect this percentage. Tuesday, we'd expect this percentage. Wednesday, and so on and so forth. And these expectations are based on the information that the motel owner provided us. And all we're doing here is, again, we're summing what the motel owner provided us, and then we're dividing each observational value divided by its total sum. So these values together up here, sorry, these values together up here. Sorry, let me reassign this. These sum to 155. So 20 divided by 155, 28 divided by 155, 18 divided by 155, and so on and so forth, provide us with those percentages. And we can, totally skip and sidestep this particular step if we just run this bit of code here. So you could either rescale them yourself and choose rescale p equals false, or if you don't want to be difficult, you could just do it like this, and there you are. This rescales these for you, making this step completely redundant. So if you're given percentages, you can just run your code such as this, where you have the percentage, your observations, rescale equals false, or if you're given observations, not as a percentage, results, observations, you would choose rescale equals true and run this code here, and this will turn these values into percentages. All right, so let's go back to our slides here. All right, so we're going to close with the chi-square homogeneity of proportions. So the test for homogeneity of proportions compares the distribution of a categorical variable across different populations or groups. It assesses whether the proportions of different categories are the same across groups. So the research question is, are the proportions of the categories the same across different groups or populations? And here's an example. Are the proportions of people who prefer different types of music the same across different regions? And as you can see here, we have more than one particular row category and column category. So in this example that we're going to do here, we're going to test for differentiation of proportion of school employee role, we have general faculty, professor, adjunct professor, custodian, and we're going to test that against job satisfaction, whether it be satisfied or unsatisfied. And we're going to use a chi-square test for homogeneity of proportions. Alpha value equals 0.05. So in this case, here is our null hypothesis and our alternative hypothesis. For the instance of null hypothesis is going to be the proportion of the categories are the same across different groups. And the alternative is the proportion of the categories are different across groups, okay? And for our particular example we're doing here, it's going to be the proportion of individuals satisfied in their roles, is being the roles, is the same across different groups. All right, so we assume that general professors, adjuncts, and custodians are just as satisfied or unsatisfied with their roles. So each one of these individual employee roles, they share the same amount of job satisfaction. The alternative is the individuals in their particular roles, they don't share the same job satisfaction. All right? So we're going to do this in RCommander. So we've collected our data from different individuals in different roles in a university. We are their statistician. So this is general faculty. So there's 150 total general faculty. 130 of those general faculty are satisfied with their position. 20 are unsatisfied. For professors, 30 are satisfied. 20 are unsatisfied. And you can see the rest here. But it's important to know that these will sum to the total number of individuals within a role. So there's 30 total custodians that we surveyed, 100 total adjunct professors, 50 total non-adjunct professors, and 150 total general faculty. So here's how we're going to apply this particular methodology in RCommander. So we go to statistics, contingency tables, enter and analyze a two-way table. We have to put in the number of rows on the slide bar. How many rows? How many columns? Well, we're working with two columns because we have satisfied and not satisfied, and we have 4 rows. General faculty, professors, adjuncts, and custodians. So we go ahead and put that information in here. All right, so 130 general faculty members were satisfied, 20 were not satisfied. So again, go to table, slide this to 4, slide this to 2. That provides you with 4 rows, 2 columns. You have to enter textually what you want in each one of these column categories and row categories, and then enter the numerical information as well. Then click statistics. We don't need percentages. I mean, you can select these as you see fit, but typically we don't need percentages. And we're going to be running a chi-square test of independence. However, the appropriate terminology that you're going to be using when you're reporting your results or detailing which test you selected as appropriate for your particular needs, you're going to state homogeneity of proportions, but when you're selecting the tab, you're going to select chi-square test of independence. Here's your output. And within the description of this video, you can find the code if you wanted to do this in a matrix directly in R Studio or the R coding language if you don't want to use RCommander. But in any event, that will not change the output. The output is right here, which is pertinent to our APA format and our results. So as you can see, here is our R square. Why do I keep saying R squared? Here is our chi-square value. Our chi-square value, okay, is right here. Here's our degrees of freedom. Here's our p-value, which you can see is less than our alpha value of 0.05. So the p is low, the null must go. So we're going to reject the null hypothesis. And as such, we're going to say a chi-square goodness of fit test was performed to assess a model of expected frequencies against observed frequencies. The relation between these variables was found to be significant. So it's found to be significant. Here is our x square, or our chi-square. Degrees of freedom was 3. 330, that's the total number of individuals observed. So it's faculty plus professors plus adjuncts plus custodial staff is 330. Here is our p-value. It was less than 0.01. And here is our chi-square value. So what does this really say then? Well, what it's saying, if we reject our null hypothesis, we would say that the proportion of individuals satisfied in their roles is not the same across different groups. So general faculty, professors, adjuncts, custodians, they don't all have the same amount of satisfaction as it relates to their particular roles. So they don't all feel the same way as it pertains to satisfaction in their role type. And here is the code. It's in the video description if you wanted to do this as a matrix in R, not using RCommander. And there is our output. And here is the findings stated for our particular example. A chi-square test of homogeneity of proportions was performed to examine for categorical differentiation between individual job roles and job satisfaction. The relation between these variables was found to be significant. And then, your various findings. So I hope that you were able to take something away from this video. If you made it to the end, congratulations. This was a long video, but it was an important video, which is why it had such a amount of length to it. Please like and subscribe if you haven't done so already, and best of luck with your research, your coursework, or your class. I hope to see you in the next video. Take care.